Today we are going to move to another subject of vector analysis. Before we discuss the vector analysis, I would like to give you the second homework. The second homework is the regression analysis. Since I already provide you the data sets, right? A zip file, there are two. In the zip file, there are four, I believe, four Excel files, and there's one of the Excel files called a regression analysis. So please repeat what we have done in class, and repeat the calculation process, and try to finish simple regression and the multiple regression before next class. And submit your Excel file to the iSchool system before next class. So the due date will be the next Wednesday midnight. Okay. I already set up the time, so don't forget. Actually, you can use the data. Try to finish by yourself, and do not use built-in function. But after you finish your calculation, maybe you can use the Excel built-in function to check your result if it's correct or not, because you need to finish the same problem. Of course, the data will be different. The similar problem in your midterm test, but you cannot use the built-in function in Excel. You have to calculate the regression analysis step by step. Okay, so that's the purpose. So you will know how to, what's the theoretical background regarding to the regression analysis, what's the meaning of each step. Okay, so that's the purpose of the assignment. The vector analysis is a very useful technique in the data science. Although the vector analysis has been developed for a long time, I think it should be at least maybe a half century, and but this technique is very, although it's linearly function, but it's very useful whenever if you collect a lot of the huge data, big data, you collect lots of the variables, but for so many variables, and then you try to reduce those variables to maybe if you collect or maybe hundreds of different variables, and then maybe only some of them is useful. Most of them maybe is not related to the dependent variable. So we can use the vector analysis, try to extract or condense or reduce the variable to certain amounts of variable, maybe reduce to the 3-dimension or only 2-dimensional, so we can see the result in the graphics, or the 3-dimensional, reduce the variables, and then still keep most of the variance in the original data. So that's the purpose of the vector analysis. Especially vector analysis can be combined with the current machine learning methods. So it's very useful techniques. Whenever you try to reduce the number of variables, it's very useful. And another advantage is that after we reduce or project the original variable to another set of a system, the new set of systems, they are orthogonal. Orthogonal means that the inner product should be equal to 0. Okay, so that's the and they are independent each others. So that's the physics of meaning. So that's very useful techniques whenever we use the vector analysis. So although this is a very traditional technique, but it can be combined with many other advanced techniques like the many machine learning or AI algorithms. You can combine these techniques with other advanced nonlinear systems. 这个因子分析虽然是很传统的 统计学的一个技术，那个资料分析的技术，但是它非常有用，就是说它可以把很多的变数缩减到一定数量，就表示你收集了 big data， 收集很多数字，但是呢，这些数字很可能有一些是没有用的资讯，很多变数啦，一大堆变数，收集了一大堆速度啊、温度啊、电压、电流，很多数，那很可能只有其中的某些变数是比较比较有用的所以你可以用这个因子分析呢，把原来的变数呢缩减到也许是一定数量，也许变成5个、4个、3个，甚至2个。变2个的好处就是说，你可以把它原来的资料呢投影在一个平面空间里面去，那你就可以在平面空间里面可以看到它的分布的状况是如何，这样可以视觉化另外好处就是你把它缩减资料之后呢，那你这个每一个变数呢，也许原来的变数呢，它彼此之间是interdependency， 就是它彼此是有相关联性的。可是你把它投影到这个新的坐标系统之后呢，它会变成一个正交的关系。所以正交关系就是它们彼此是相互独立的，就是它们是就是每一个变数之间彼此是相互独立。那相互独立数学上就是就是内积是等于0嘛 ，inner product 是等于0，这个是就或者orthogonal，就是术语的话就叫做正交矩阵。Okay, before we discuss the factor analysis, we have to review the linear algebra. So this is a very basic topic or concept in linear algebra. Okay, so how to find the eigenvalue and eigenvectors. So, for example, I just used this very simple example to illustrate the eigenvalue and eigenvectors. So, if you forget linear algebra, you should go back to look at your textbook regarding to the eigenvalue and eigenvectors. Okay. For example, there is a vector. There's a matrix, A matrix. Okay, this is the 2x2 matrix. And then if we want to find eigenvalue and eigenvector of A is equivalent to find a vector A, and then to let this matrix multiply this vector A is equal to a lambda. Lambda is a constant, and multiply A. And then if we can find this vector A, then we will call this A is eigenvectors, and then this lambda is called eigenvalue. So this is the definition of eigenvalue and eigenvectors. Okay. And since this is the definition, for any vector or any matrix, if we can find a vector this matrix multiply some vectors is equal to a constant multiplied these vectors. So then we define this A is called eigenvector, this lambda is called eigenvalue, and then we can move to the, if you forget, you should go back to see your linear algebra textbook. And then since if we can find this one, we can move the right-hand side to the left-hand side. So if this, you can find this one, then the determinant, what's the determinant? Well, you still need to go back to find your linear algebra. The determinant should be equal to 0. So it means the determinant should, if this determinant, it means the determinant A minus lambda. I is identity matrix. Identity matrix should know what's the identity matrix. If you do not know identity matrix, well, there's a problem. Okay, the A is identity matrix, so this one should be equal to 0. This means that this determinant should be equal to 0, and then we can solve these polynomial equations. So it will be equal to this one multiplied, this one minus this one multiplied. This one should be solved, these polynomial equations should be equal to 0. So it equal to lambda minus 0.5, and then so this is the equations. If we actually this is the trace the A, the the trace of A means the sum of the diagonal elements. Okay, determine. Okay, the determine A means the determine. Well, I do not know what's how to translate the determine in Chinese. Determine 中文有翻译啊 ？determine 没有，我忘了怎么翻译。是啊，对，行列式的 determine 叫什么？行列式值啦。determine 就是行列式的值嘛，只是有特有名词吗？哇 ，OK， 就行列式的值就对，叫 determine 嘛，对不对？它的 determine 要等于零，就这个我们因为 determine 就we move the right hand side to the left hand side, and then it should be equal to 0. If this is equal, it means this is determined. It should be equal to 0, and then we can solve this polynomial equation. So after we solve this polynomial equation, because this is the lambda is the power 2, so we will have a two roots. So we will get a two set of equation. Okay, the solving the polynomial this polynomial equation, we will get lambda 1 is equal. The first solution lambda 1 is equal to 1. Then it means that lambda 1 is equal to 1. It means that this matrix multiplied these vectors will be equal to 1 multiplied A1, A2, right? So we can solve this equation. So this is matrix multiplied this one, sum product of this one. So 0.55 multiplied A1 plus 0.35 multiplied A2. Multiplied A2 should be equal to A1, right? So based on this equation, and then we will know the ratio between the A1 and A2. So the A vector will be 6, 8 or 3, 4. So and his union vector will be 3 over 5 and 4 over 5. The union vector means his length is equal to 1. Okay. So this is we solve the first set of solution. So we find the lambda 1 is the first eigenvalue is lambda equal to 1, and the first eigenvector is the union eigenvector will be 3 over 5 and 4 over 5. Okay, so this is the first set of equation. And then the second one, of course, the polynomial is we have two roots. The second equation will be lambda equal to 0.25, and then we substitute the same idea. We substitute the lambda to here, and then solve the eigenvectors. So based on this equation, then we get this one. So we got the A1, A2, the ratio between A1 and A2 is -4 and 3. So you will see the first lambda 1 is equal to 1. This corresponding eigenvector 1 is equal to 3. The union vector, okay. And the lambda 2 is equal to 0.25, and the A2 is equal to -5 over 4 and 3 over 5, right? So these two eigenvectors, they should be orthogonal. Okay, you can see if these two vector inner product A1 inner product A2 is equal to inner product. You should know this one multiply this one plus this one multiply this one, so it should be equal to 25, 12 plus 25, 12 is equal to 0, right? So his inner product should be equal to 0, and the geographic meaning is 3, 4 is 3, 4 is approximately this one. The 3, 4 is approximately. So this is the first. So this is the first eigenvector. The second eigenvector will be minus. Right, and this is also gamma. Okay. This means they are also gamma. So this is a two new set of system. This is original system X and Y, but the eigen value 1, the lambda 1, this corresponding eigenvector is the unions of eigenvector. Is this one is this direction, and lambda 2 is 0.25. This corresponding to eigenvector is this one. So the inner product is equal to 0. And the geographical meaning means this is the rectangular. These two vectors, they are rectangular. Or in the physics meaning, it means these two vectors are independent each others. Okay, 就是它每一个就是2乘2的矩阵就会有2个特征向量，那3乘3的当然就会有3个特征向量，4乘4就会产生4个特征向量，因为就会变成解一个是就是多项式嘛，就是每一个就是如果是3乘3就会有 lambda 1、lambda 2、lambda 3，所以就会产生3组的特征向量。那3组特征向量它们也是一样，彼此之间会相互独立。相互独立的意思就是它彼此之间的它们的这个特征向量呢的内积是等于0的。如果我们另外一个象限呢，可能是拉出来，就它们彼此之间是相互独立的，或者垂直的。So that's the geographical meaning and the mathematical meaning regarding to the eigenvalue and eigenvectors. Okay, so this is the basic concept. A very quick review. Just use one very simple problem to review the eigenvalue and eigenvector. So you had better go back to read the textbook of your matrix or your linear algebra textbook. Okay, actually we have the concept of the eigenvalue and eigenvector. So we know in eigenvalue and eigenvector problems, so it means, okay, is the A, we try to find a matrix A multiplied a vector A, we try to find this matrix multiplied some vector is equal to a constant multiplied the same vectors. So we call this is eigenvalue, this is eigenvector. So that's the idea, right? So if we can find this lambda and this A, then this lambda is called eigenvalue, A is called eigenvectors. And before we conduct because there are some before we do the vector analysis, because most of the vector analysis we use the principal component analysis to obtain their vectors analysis. Because after we got the PCA, principal component analysis, we can use the x-axis rotations, iteration, to get another set of the equation, And then in that set equation, we call this the factor analysis. But the basic idea, most of the idea is very similar. So we will start from the principal component analysis. Okay, the principal PCA is looking for a set of variables which are linearly combination of the original variable. It means we will find an original variable maybe is the x1, x2, x3, x4, x5, and then we will try to find another set of the variable maybe became the y1, y2, y3, y4, and then to try to project the original data from the x1 to x4 system to the y1 to y4 system. So that's the meaning of the principal component. And the characteristic of the PCA is this new system, they are orthogonal. Okay, they are orthogonal. Okay, the set of new variable will still keep the original information and independent each other. Independent each other is means orthogonal, just like this way. Okay, they are in the vector in the geographical meaning is right. Here is the right angle. Okay, or the mathematical meaning is the inner product that is equal to 0. So, and we try to use the fewer principal component factors to represent original variables. So that's the main purpose of the PCA principal component analysis, as I just mentioned, because in today's era, we have lots of the sensors to collect many data, and so many data. Maybe some of them is useless. Only some variable can be used. So we can use the PCA to reduce original variable. Okay, original variable maybe is 10 variable, but we reduce those original variables to 2 variables, and then we still keep most of their original information, and then we can use the fewer variable to represent original many variables. So that's the purpose of the PCA. Or so we will use a fewer principal component factor to represent original variables. Okay. But we still need to go back to the theoretical part because that's still very important. Assume we collect the persons, use this one to illustrate the meaning. Okay, if we collect a person's weight and height and 2 variables, right? We collect the person's weight and height, and then we try to use 1 variable, figures, to represent those people's weight and height. So it means we will try to use we collect 2 variables, but we just want to use 1 variable to represent these 2 variables. Okay, so it means we are looking for the A1 and A2, and to that the variance of the Y is equal to a linear combination of the A1, X1 plus A2, X2 is maximized. Okay, so that's the purpose, right? So, but since so that's the way we still keep the variance means the information or original information, right? So we are trying to this is original variable x1, x2. The x1 maybe is the weight, x2 maybe is the height. So we will try to find a new variable called the figures, and this new variable, this y, is equal to a1 multiplied x1 plus a2 multiplied x2 to represent one of the figures. Just like when you do the physical check, they will always tell you what's your BMI value. 就是好像就各位去体检，都会告诉你一个 BMI 值嘛。那 BMI 是什么意思？我忘记它定义的。BMI 是什么？ 可能它是什么体重跟身高，然后一个公式，反正就把它算可以算出一个 BMI 值。也就是说，我想要用本来是一个人收集一个人的身高跟体重，有2个变数嘛。可是我想说，我能不能用一个变数就来代表这个人他的身高体重大概的状况？我就可以从一个变数，我就可以大概知道这个人到底是高矮型、胖瘦型，他大概是怎么样。所以我就找 Y， 那我们定义说，这个 Y 呢，我就把它名字叫做体型好了。体型我就是随便掰了，讲到体型，那我就希望，什么体型等于 A1 乘上多少他的身高，加上 A2 乘上多少的体重，这个数值就代表说，这个人他的体型是多少，就类似 BMI 的概念是一样的。BMI 可能是多少乘上你的身高，加上多少乘上你的体重。然后可能经过什么，还有什么公式我不知道，各位回去可以去查一下 BMI 的公式 ，whatever， 意思是同样的概念，对不对？那它的好处是什么？就是说我要找出这个 A1 跟 A2 这2个这2个系数嘛，然后可是让这个变 variance， 就是它原来变数，就身高体重原来的总的变异量，总变异量就是它的 variance， 就是变异数。它的 variance 应该知道，就是第一堂中有介绍，就是怎么定义它的一个变数它的variance， 对不对？就是看它分散程度嘛。所以它保持原来的 variance， 可是它是变成一个新的。我本来是2个变数 x1 x2 的，我现在变成一个变数，就是用体型来代表你的身高跟体重，就类似你把它想象成，我用个 BMI 值来代表你的身高体重多少。所以我只要从 BMI 值，我就可以判断说，你这个人大概是身高过高太瘦了，还是这个太胖了，然后怎么样 whatever， 就是我可以从 BMI 值来判断，就从体型我定义一个新的变数的体型。那但是保持原来的 variance， 就是 x1 跟 x2 它的 variance 这样，它的基本的概念是这样。那希望这个 variance 要最大，要 maximize 是最大。也就是说呢 ，maximize so the mathematical meaning means that we are trying to find the variance of the CY. We try to find this new variable. Their variance has the maximum. Still keep the original variable as maximum. So because this is the y, so this is the vector. So the union vector will be his length should be equal to 1. So this might be his union vector. This is maybe his union vector. Okay. So this is this means the union vector means his length equal to 1. 单位向量是指的它的长度是1嘛，这个单位向量。所以任何这个方向的都可以当做它的一个基底。这个基底是什么？就是回去看一下那个线性代数，就是任何一个这个方向跟任何这个方向的向量都可以当做它基底。只是说我们习惯上我们就用单位向量来表示，所以我们就是 CY 就是代表任何一个这个方向都可以了，理论上是都可以的。So we take the maxima of the variance of CY, and then this is from the statistic, right? The variance of CY it will be equal to C squared multiply variance Y, right? And then we try to that this is the union vector. So we set the A1 squared plus A2 squared is equal to 1. This means it is the union vector, okay, not the all of the possible vector in this direction, okay. 我们希望能够找它的单位向量就好，不要，因为理论上是任何一个向量在这个方向，在这个方向都可以了，都可以。但是我们希望找到它的单位向量。Okay, so the variance y, so we derive the variance y is equal to, I just substitute this equation, right? This equation into here, right? So you take the variance of the A1 x1 plus A2 x2, right? So this is very simple. I just substitute this y, this is equal to y, right? So I substitute here, right? And this also from the calculus, okay? This is also from calculus. for this variance A1 x1 plus A2 x2 is equal to variance A1 x1 plus variance A2 x2, and then this variance A1 x1 is equal to A1 plus variance A2, and then this equation, and his covariance A1 A2 x1 x2. Okay, so this is from the calculus. Okay. And then we can simplify this equation. So this is, if we define this as sigma 1, is his variance. The sigma 1 means the x1's variance. And x2, his variance, we define as sigma 2. So we can simplify this equation, this equation. And then this polynomial equation, we can also use the vector form to represent. So this is equal to this vector form is same as this equation. And then this vector form, we can use this became use this symbol. This is A vector, right? This A vector, his transpose. This sigma means his variance covariance matrix. This is his vector A, right? So it will be equal to A transpose multiply his variance covariance matrix multiply the A vectors. So this is the it's very straightforward derivation, right? So we try to find the maxima. We try to find a vector to extract most of the information in this new direction, in this new vectors, and then they have the maximum variance. Okay, they have the maximum variance. Okay， 我们就是想要说，我找到一个，我希望我把这本来是 x1 跟 x2 就一个身高一个体重，那我希望找到一个新的坐标，y 坐标，它等于一个线性组合，一个 A1 x1 加上 A2 x2 的一个线性组合。让这原来的身高体重它们的变异量投影在这个新的坐标上面去呢？假设这个新的坐标这个 y 好了，假设这个新的坐标 y 呢？假设这个 y 等于，我就希望找到一个 y 等于A1 乘以身高height 好了，加上 A2 乘以体重，乘以 weight。我希望找到这个 A1。跟 A2 是反应，就我希望找到某一个方向，这这两个的线性组合。那把原来的资料呢，这原来资料，假设原来资料是这样，原来这个资料，原来某一个人他资料身高在这里，体重在这里，可是我把它投影到这个新的坐标来。But right now, if this is original data, this is original data. His x1 is here. Here's if this is x1, this is x2. This is his x1 value, this x2 value, and then but right now we are going to project this one to this. We are going to project 把它投影到这里来，就是到这个是直角。We are going to project. This point became here. This is the y. This is the y direction. So this is his new coordinate. And then we call this value is his figure for the BMI value, whatever you want to call. 就是我把原来的我假设某一个他身高在这里，体重在这里，所以我用一个它是两个，它是坐标只有两个嘛，一个。可是我把它现在投影到这新的坐标来，那新的坐标是等于 A1 乘上身高加上我们 A2 乘上体重，它一个线性组合，事实上就找到一个新的坐标，把这个原来的坐标投影到这个新的坐标来。投影的意思就是把它这个垂直嘛，垂直过来，然后那这个新的这个数值呢，这个数值是什么？这就是 A1 加 H1 加上 A2 加 W 嘛，A1 乘以 H 加上 A2 乘以 W 嘛，然后这个数字我就称作新的一个变数，叫体型或 BMI whatever 你要叫什么都可以。OK， 我们就是要找到那个，所以 让它的这个变异量，让它投影过来，这个在 y 坐标它的 variance。So the purpose is we try to variance to that this variance, this original data in this new coordinate, their variance should be maximized. Okay, their variance should be maximized, and then after we derive this equation, this should be maximized. It means this should be maximized, right? Okay, so 那我们就推导，这个变异数，那这个变异数我一路推导下来嘛，这一路我只是把这个 y 我希望它是单位向量，所以我就 c 不要了。然后就 y， 然后就是把这个这个都从这个因为 y 会等于 a1 xy 加 a2 x2，把它带进来，然后这个把它展开，就是统计学里面把它展开之后就会变成这个式子。那这个式子，那我再定义x1 它的变异数是sigma 平方 sigma 1平方，那x2 体重它的变异数是sigma 2的平方。那所以我们就可以得到这个多项式。那这个多项式我可以把它化简成，我用向量来表示。你把这个乘开，这个向量跟矩阵你应该走，这个乘上这个加上这个乘上这个嘛，然后这个再跟它相乘，那就会刚好会等于这个多项式。那这个多项式，那这个呢矩阵形式，我把它展开形式。那如果我要简化，我用单纯向量的话 ，A 代表这个是一个 A 向量嘛，它的元素就是 A1、A2。那就刚才讲的什么34，这个是 A1、A2 嘛，那这是 A1 向量 ，this is a vector， 所以这是 A1 向量，所以它等于这个 A1 向 A 向量的T 是代表 transport， 乘上 sigma 是代表这个是什么？这是它的变异互变异矩阵 ，this is the variance covariance matrix，this is the vector A，right？ So this is the we try to find this maxima. This means we try to find this maximum. Okay, it's the same. And under the constraint, so under this constraint, we try to find the union vector. So to find the maxima, this one is equivalent to solve the maxima, this one, right? And satisfy is separate equation. OK， 我们刚刚一路推我要找出 y 它的最大的变异量，找出这个 y， 它把原来的资料全部投影到这 y 上面之后，让它的变异数是最大，就是我们的希望它是最大的，变异数是最大的这个 y， 我们要找出这个 y 多少，也就是要找出它这个线性组合 A1、A2 应该是多少，然后我们同时要希望它是一个单位向量就好了。So this A is the eigenvector corresponding to the maximum eigenvalue lambda in the sigma, and then where the sigma is a correlation metric of the variance covariance matrix. So this is the same. Actually, so that's the why we introduce the eigenvalue eigenvector in advance. This means because we are trying to find this equation satisfy subject to this constraint is equivalent to find this variance covariance matrix eigenvalue and eigenvector, and this A is equal to eigenvectors. Okay, and his maxima lambda is called the first principal component. And the lambda 1 will be the first principal component. Lambda 2, the corresponding eigenvector, will be his second principal component vectors. Okay, so that's the same idea. Okay. Okay, back to the real data here. Assume we collect a data. There are n set of data. The first objective, the x1 is, we call it x11. This is a variable 2, this is variable xi, this is a variable xp. Right? And then for each data, for the first data, it means the first object is the correspondent to the, here, this is the first index means the variable. Yeah, this the second index means which object. Okay, so this is the data set we usually have. Okay, and then we have a x1 variable, x2 variable, till the xp variable. We have a p variables. And then, if we can extend the previous example, we have only 2 variables. Right now, we will extend the same idea, the same concept to the p variable. Okay, so it's also we are looking for a y, right? This y is equal to beta 1 x1, beta 2 x2. And then beta I xi, and then to the beta p xp, right? If we use the vector form, will be the beta vector multiplied the a vectors, right? So this is the same idea. We extend the 2 dimension to the p dimension, okay? And then we are trying to find the maximum y, right? So the maximum y means the maximum beta xy. This is the beta x, okay? And then it will be equal to, because this beta is a constant, so when we use this is from the statistic, so it will become the beta transpose multiplied beta, so it's a squared, right? Just like the same idea, the calculus, the Vax is equal to a squared Vx, right? So this is from the calculus, okay? Vx is a squared multiplied v. But since this is a vector form, so we have to use the transpose and multiply, become the inner product, just like we calculate the square errors, same idea. Okay, so and then subject to his should be equal to 1. So it means his length should be equal to 1, and then this is from the I think it's calculus, right? Lagrange multiplier. So if we want to find the maximum value of this one, and then subject to this constraint, then we can define a Q is equal to this one. This is the variance X is his variance covariance matrix. We use R to represent it, and then minus lambda multiplied. This is this we move to the left hand side minus 1. So this is from the calculus. Okay, Lagrange multiply. This is, so we extend the original problem, the original problem from the 2 dimension to the p dimension, and then the same idea. All of the same. Only parts here is that we want to try to solve this one. From the calculus, we know it's equivalent to find the maximum value of this Q. The Q is equal to this one. This is because this is the R, or R it means the standardized. If the standardized data is the correlation matrix, if it's not standardized, it will be the variance covariance matrix. Okay, and then subject to this one. So this is the lambda is it's not the eigenvalue. The lambda here is the Lagrange multiplier. Okay, so it's equal to we solve this one, and then since we try to find the maximum value, so we take the partial to the beta. The partial beta, the derivative of the beta is equal to this equation. Okay, so this is the beta square, and then 2r beta, right, minus this beta square is 2 lambda beta equal to 0, right? this is from the figures， 多项式微分嘛，把它微分之后就会变2r 贝塔嘛，这是2兰达贝塔要等于0嘛。Then we can simplify this 2 can be deleted. It will become r minus lambda I multiplied beta equal to 0, right? So it will become this one equal to 0. And then this form were very similar. It's the same, right? Do you remember? In the beginning, the A matrix multiplied a vector is equal to lambda multiplied A. This is this formula, and then if this is this lambda is called the eigenvalue. This A is called eigenvector. So this should be equal to 0. So right now it's the same, right? Right now we got the same formula. This is the A matrix multiplied lambda. I identity matrix multiplied a vector beta is equal to 0. Right? This is the same situation as we solve the eigenvalue and eigenvector. So then we can solve. We can try to find the R. The R is the standard data. Then this is correlation matrix. If this is a non-standard, it will be the variance covariance matrix, which is equivalent to find the R's eigenvectors. And this lambda will become the eigen value. Okay, the same. So that's the if we extend the same concept to the p-dimensional problem, we found okay, wow. If we try to find this linear combination, this beta, this linear combination, this beta, the coefficient of beta, actually is equivalent to find the R matrix, his eigenvector. And this eigenvector will be this beta vectors. Same, and that is, if we extend, it will become the beta 1, x1, beta 2, x2, and until to the beta p multiplied xp. So that's we got a very important conclusion here. So to find a linear combination, of new y, to that this y has the maximum variance, and then this coefficient, this a1, a2, a3, a4, or the beta 1, beta 2, beta 3, beta 4, this value is just these vectors, okay? It's just exactly to same as to find his variance, the original data, the variance covariance matrix, his corresponding eigenvectors. 我们就从刚刚的那个二度空间的问题呢，我们把它推展到 p 次元空间。刚刚身高体重，我们就从身高体重我找到一个体积，那是在2次元空间，我就可以找到A1 A2 这样。那我把原来问题我把它扩展到 p 次元空间，那也就是说，假设有 p 个变数，x1 一直到 xp 那我现在就要找到出这个 beta 1 beta 2，也就是这边的 A1 A2 意思是一样。beta 1这个就有点你把它想成回归系数一样，我要找它这个系数是多少，我要找出这个 beta 是多少，这个是我们的目的。那我就一路推导下来，就是找到一样 beta， 就是要找到这个 maxima 变异数最大的 y， 这个新的变异那个新的坐标系统 y， 然后找到那这边它一样，这都跟刚刚二次元二次那个刚刚的那个二度空间的问题是一样的。那这边是从这里跳到这里是微积分里面的，就是我们要找到它的极大值，然后有一个限制式，我们就用这个 Lagrange multiply， 应该是微积分在后面的部分。微积分里面你要找它的极大值，要某个限制式的话，我们可以用这个式子，就变成解这个式子。那解这个式子你要找它的极大值，我找极大值或极小值就是取微分嘛。 这也是微积分里面，我在对贝塔做微分，微分之后它就会变成这样子，微分必须要等于0嘛，所以这等于0，那我就就这个把它微分之后就变成这个，所以我把这2跟2消掉，然后再把它移过来一下，就把它重新整理一下，就发现变成这个形式。那这个形式就跟刚刚一开始我们讲的一个这个特征值、特征向量的数学形式是一样的。这 R 就是 A 向量嘛，就是讲任何一个向量 A 减掉 lambda 这单位矩阵乘上某一个向量，刚好如果会等于0的话，那我们就知道这个 lambda 就乘上它的特征值。这个贝塔找出来就是什么？就是它特征向量。那贝塔就是我们要找的这个特征向量这贝塔就是特征向量。所以意思也就是说，那我要找这个新的这个坐标 y， 让它的在这新的坐标 y 里面有最大变异量的这个系数，这个线性组合的这个系数呢，其实就是在找它的特征向量的这个系数，是一样的东西，这样子。OK， 我们先休息一下。前面用到了这个线性代数还有微积分的概念所以如果你线性代数忘记，特别是特征值、特征向量这一部分，回去翻一下你们的那个看可能是管数吧，有的学校是叫管数，有的学校是叫线性代数。那还有这个只有这边微积分，就这里是微积分了就这个是，当然这个很简单，这就是 Lagrange multiply， 就是在微积分比较后面的。就是你要找它极值的时候，就是就是这个或者是你到那个 ChatGPT 问他也可以你自己看一看，因为这边用到的观念比较多一点，就是用到线性代数的概念，要用到微积分的概念。